Hello all. In this video lecture, I am going to simulate the cyclo converter. So, a cyclo converter will convert the fixed AC voltage to a variable AC voltage with variation in frequency also, which means we can vary both voltage as well as frequency in case of cyclo converter. But if you see the last video where we have varied only voltage, not the frequency. So that is called AC voltage controller, right? So now in this video lecture, we are going to vary both voltage as well as a frequency, right? So before going to start the simulation process, let me have the overview of this cyclo converter. So now you can see cyclo converter is a device which converts fixed AC to variable AC with variation in voltage as well as frequency. So based upon the relationship between the input frequency and the output frequency, cyclo converter can be a step down cyclo converter, it can be a step up cyclo converter. In case of step up cyclo converter, the output frequency is more than the supply frequency, but in case of step down cyclo converter, output frequency is less than the input frequency. Now in this video, I am going to explain about step down cyclo converter. I will take the supply frequency as 50 Hz and I will try to get the output frequency as 25 Hz. Right? So this is what I am going to achieve, do now. Right? So there are two types of configuration for the cyclo converter. One is midpoint type cyclo converter and one more is a bridge type of cyclo converter. Right here you can see the circuit configuration. I don't want to go into detail of this one. So here you can see bridge type, midpoint type configuration where you can see center type here, and here you can see bridge type cyclo converter. So the ultimate aim of these two converters is to convert the AC to a variable AC, fixed AC to a variable AC, right? And you can see the notation P1, P2. That is P1, P2 are triggered to achieve a controllable positive output voltage waveform. And if you want to achieve the negative output voltage waveform, then I can trigger N1, N2. Similarly, here you can see this bridge. I can see the thyristor notation P1, P2, P3, and P4. Right. So this bridge 1 is used to have controllable voltage over positive half cycle. And this bridge, you can see one more bridge, they are connected in anti-parallel. So where you can find N1, N2, N3, and N4, right? These devices are triggered to control the negative half cycle of AC waveform, right? So I will consider a bridge type of configuration where you'll be having 8 thyristors, right? And I will try to convert the 50 Hz supply to a 25 Hz output frequency. And also I am going to control the output voltage waveform. As you all know that by triggering the thyristor as respective time interval, we can control the output voltage. During positive half cycle from 0 to pi, P1, P2 will be in forward bias condition, these two devices, whereas P3, P4, they are in reverse bias condition. Similarly, during this positive half cycle, N3, N4 also in forward bias condition, and N1, N2 will be in reverse bias condition, right? And when you see during negative half cycle, so P3, P4 will be in forward bias condition, whereas P1, P2 will be in reverse bias condition. In a similar way, if you see the second bridge, where you can see N1, N2 will be in forward bias condition, N3, N4 will be reverse bias condition. So that is what we have discussed during the class session, right? So now here, if I consider 50 Hz as the input frequency, So 1 by 50 is the time duration, which is 0.02 second. That is 20 millisecond. So up to this particular point, you will get 20 millisecond. Up to this particular point, you will get 40 millisecond year to year, 0 to 4 pi. So which means for 25 hedge, 1 by 25 means it is 0.04 second. So to have 25 hedge as output frequency, so it will complete one cycle in 40 millisecond. That means during to get positive half cycle, it will take 20 millisecond. Remaining negative half cycle, it will take 20 millisecond. That means if I take the fundamental voltage waveform, it will be something like this, where you can see the first two half cycle as positive half cycle and second two half cycle are negative half cycles. So which is completing one output cycle. In one output cycle, we can see two input cycle, right? Because the input cycle is for 50 Hz, whereas output frequency is for 25 Hz, right? So now I will go for the simulation part, right? So let me share the Matlab model now. And I will click on this new model. Then I will go for Simulink model. Now to do the simulation, this is the procedure you need to follow, right? First, I will open the Matlab, then I will click on the Simulink model. Then you need to go to library browser and search for the required element. Like if you want resistor, you can go for RLC series branch. If you want to measure the current, you need to go for current measurement block. If you want to see the output voltage waveform, you need to go for output voltage measurement block like this. So keep on adding them to a new model. Make the connections as per the circuit. Just now we have seen. In order to measure the voltage, current have voltage measurement block across the component. To measure the current, we need to measure the current measurement block in series the element. And to observe the waveform like voltage and current scope at the output terminals for measuring the block, right? Then here you can have the theoretical calculation. So to do the theoretical calculation, this is the expression for RMS output voltage in case of resistive load, and this is the expression for RMS output voltage in case of resistive and inductive load. So substitute different values of firing angle like 0, 30, 60, 90, and 120, and find out the corresponding RMS output voltage using this formula, right? So here take beta equal to 220 degrees, right? So for this 50 Hz and 50 ohm and 50 millihenry, you will get 210 degrees as the beta, right? So you can calculate the RMS output voltage at 0 degree, 30 degrees, 60 degrees, 90, 120, 150 like this, right? Now with this background, I will start the simulation process. Right now, I will go to the Matlab model. Right here, you can see the new. So here I will go for Simulink model. Then the Simulink model will open. Right. So now here I need to build a Matlab model. Right. For that one, I need to go for browser. Then I will add one by one. First, I will take AC voltage source. All right, so this is what AC voltage source. Then here I will go to the untitled model where I can see the AC voltage. So now AC voltage input is 230 volts. Frequency input frequency is 50 Hz. Right. Okay. Then again I need to go for what is called Matlab browser. Simulink browser. Then I will add one by one. So then I will take thyristor, detailed thyristor model. I will add that to the new model, new untitled model. Then I will take this called pulse generator to give the firing pulses to all 8 thyristors. So we'll be having 4 firing pulses. Then I will go for voltage measurement block. Voltage measurement block which will measure the current, and you can see the voltage wave shape. Then I will go for current measurement block. And then series RLC branch. So that is what our load. Okay, now, and I will also add scope to see all the waveforms. Then to run the block, I will go for power V. This will run the complete model. Right, so here I can see here I can see all the elements which I have added just now. So now this is, I will keep this in discrete mode, right? And so I will collect all the elements from this block, right? So now if I see so now you can see this is thyristor P1, P3, P2, P4, right? Same thing I am going to see there, P1, P3. Now I will rename this thyristor. I will rename this thyristor to P1. Then here will be having P3, P2, P3, and P4. Right. So now I will connect them to form a bridge. Right. Same thing you can see here. P1, P3, P4, P2. Similarly, you can see 4 more thyristors like N3, N1, N2, N4. So let me go to the untitled block and so I will take, right. So now it is N1, N2, N3, and N4. N3, N1, N2, N4. Right. So now I will join the anode, cathode to anode, right? And in between, I am having a what is called load. Now we'll place a load, and load is, I will take first initial, I will take a resistive load with value 2 ohm, right? Then I will connect this anode, and cathode. Then I will connect a load to this bridge. Thereafter, like this, similar circuit I am going to build here, which I have shown you. This is resistive load, right? So this is resistive load. Now I am going to connect a AC supply to the bridge. Same AC supply I am going to connect here. right? Then now I am going to apply the firing pulses. See, just I want to recall these things here, which is very, very important. Now, I need to get the output voltage, which is a variable one, and the frequency of the output voltage should be a 25 Hz. So, which means I need to trigger this P1, P2 at a time at some alpha. Then P3, P4 should be triggered at pi plus alpha. And N3, N4 should be triggered at 2 pi plus alpha. Similarly, N1, N2 should be triggered at 3 pi plus alpha. So to achieve the pulses like this, I need to take two output cycle, right? So as I told you, to complete two cycle at the output side, so that means 720 degrees it requires, and that is for 0.04 second, right? So if I want to trigger for 30 degrees, then I need to write it as 0.04 divided by 720 into 30 degrees. So that value I need to adjust here, right? That value I need to adjust here in the pulse generator. So now same value I am going to keep here. One pulse width, it is 0.04. It is pulse width percentage is 2. Now here it is 0.04 into 30 degrees, right? Let me take the bracket here. Divided by 720 degrees, because this is for 2 cycles. So P1 and P2 should be triggered the same time, right? So it is given to P1 as well as P2. Sorry, should be corrected to gate terminal, right? Okay. Now, after 180 degrees, again I will go to the that PPT so that you will have some idea. So after 180 degrees, P3, P4 should be triggered. So now I will go to the untitled model. Now I will take the same pulse generator from there. We'll copy here, and now after 180 degrees, right? So it is 30 plus 180 degrees. And it is given to P3 as well as P4. Now, if you see, after again 180 degrees with respect to P3 and P4, N3, N4 should be triggered. So let me go to the untitled model. N3, N4 should be triggered. So I will take this block and I will give firing pulse to N3 as well as N4. And now it is plus 180 degrees because it's 2 pi plus alpha, right? Now at last we are going to provide firing pulses to N1 and N3. Now it is 3 pi plus alpha. If you see the waveform, so 3 pi Matlab 3 times 180 and plus alpha means 30 degrees. So this is what the pulses we have applied. Now to see the current, I will connect a current measurement block in series with the element that will give the current. And to see the voltage, I will connect a voltage measurement block parallel to the load, right? And I will take the scope now. So scope parameters I need to adjust. So there I need to take 6 axes at a time. And I will uncheck here. Then I will adjust to black color and I will increase the length, width of the line. Okay, let me increase the width of second line also, so that you will get a good result, right? So first I will measure the input waveform, input voltage waveshape. Then I will see the firing pulses given to P1, P2, then I will see the firing pulse given to P3, P4. Thereafter, if you see, it is N1, N3, sorry, N3, N4, N3, N4, then N1, N2. At last, I want to see the output voltage waveform, and both output voltage waveform and output current waveform I want to see. To see these values wave shape at the same time, I need to go for mux. Mux, the input to the mux are current, output current and output voltage. And directly I can connect to the scope like this. Now I will run this model. I will run this model for 0.1 second. Right, let me see. Oh, here I can see the wave shapes. Simulation results now. Here you can see the simulation results at 30 degrees. Now this is at this particular point, P1, P2 are triggered. Here P3, P4 are triggered. Here N3, N4 are triggered. And finally N1, N2 are triggered. And now you can see, as I told you at the beginning of the session, that thyristor P1 to P2 or P4 are used to get a positive output voltage. So during this interval from here to here, you can see the positive output voltage and the positive output voltage for first 2 half cycle. And thyristors N1 to N3, N4 are used to get negative output voltage. So you can see here N3, N4 are triggered and you can see the negative output voltage waveform. Similarly here N1, N2 are triggered, you can see the negative output voltage waveform. And due to resistive load, the current and the voltage, they are in phase, right? They are in phase. That you can see here easily. Where red color is for voltage wave shape and black color is for current wave shape, where you can see the voltage and current, they are in phase. They are in phase. And here to here it is taking one complete input cycle. That means if you see, it is for 2 milliseconds, 0 to 2 milliseconds. So in one input cycle, it is generating only the positive half cycle. And for the remaining, for the remaining one cycle, if you see the output cycle, it is providing only the negative half cycle. That means if you see the output side, it is completing one output cycle in 40 millisecond. So 1 by 40 millisecond is 25 Hz. So the output frequency is 25 Hz and the input frequency, supply frequency is 50 Hz. That means this cyclo converter is converting 50 Hz to 25 Hz. So which means the output voltage, output frequency is less than the supply frequency. So it is called step down cyclo converter. So this is at alpha equal 30 degrees. Now you can run the simulation at any value of firing angle like 60, 90, 120. You can go up to 180 degrees, less than or equal to 180 degrees. So let me go for some other firing angle. So now I will go for 30 degrees firing angle. Sorry, 60 degrees firing angle. So I will copy this complete model. I will copy this complete model and I will build the circuit. Sorry, I will paste the circuit same here. So now here I can see the other cycle, other circuit, and the circuit I am going to operate at alpha 60 degrees. So just I want to measure the output voltage. If you want, you can have the same circuit. Okay, now I will place the scope also here. Right. So now this scope will show the wave shapes at alpha 60 degrees. Now just I will replace the 30 with 60. Here also I will replace this 30 with 60. Similarly, for the negative group thyristors. Right, so now I will replace the 30 with 60. Now this way, this scope should show the firing pulse output voltage waveform and the thyristor voltages at alpha 60 degrees. Here you can see. So this is what 60 degrees. Right. Similarly, you can see at other firing angle also. Let me go for 90 degrees now. So where I need to replace 30 degrees with 90 degrees. So here you can see the same circuit. Now instead of 60, I will replace the 60 with 90 degrees. Similarly, at this particular point, replace 60 with 90. Replace 60 with 90. And here also, replace 60 with 90, which will give the result at alpha equal to 90 degrees. So you will get only half cycle. You can see only positive half cycle. You get half of the output voltage, half of the input voltage, right? So this at alpha equal to, yeah, you can see here. This at alpha equal to 90 degrees, which means if you apply 230 volts as the input voltage, the output voltage will be around 115 volts, because we are getting only half of the cycle, half of the positive half cycle and half of the negative half cycle, right? So this will be your output voltage. And if you see the frequency is 25 Hz, because this is completing one cycle here, which is for 20 millisecond. Now, so during 20 millisecond, we are getting only the positive half cycle, and remaining 20 millisecond, I am getting the negative half cycle, which means if you see the output cycle, it is completing one cycle at 0.04 second. So 1 by 0.04 second will give 25 Hz. 25 Hz, whereas here it is 50 Hz. So which means it is converting the frequency from 50 Hz to 25 Hz. That means it is called a step down cycloconverter. Like that, I can go for any value of firing angle. I can go for 120, 150, up to 180 I can go. So now I will show you all the waveforms at the same scope with different firing angle. Now I will take one scope here. All right. So let me take the 4 instead of 6 cycles. I will take 4 cycles only now. Right, and right. So now this I want to first I want to see the input, right? Then at 30 degree, 60 degree, and at 90 degree. All right. So now we'll simulate the circuit, and now this scope you can see this scope you can see. Sorry. Right. So now this is the input voltage waveform. So for 50 Hz, it is taking 20 millisecond to complete one cycle. And when you see the output waveforms, so here you can see it alpha 30 degrees, where you can see only positive half cycle during first 20 millisecond, and only negative half cycle for the remaining 20 milliseconds. So 20 plus 20 is 80 millisecond, 40 millisecond. So 1 by 40 means it is 25 Hz is our output frequency. And we are controlling frequency here. Similarly, you can control the voltage also by controlling the firing angle. So this is at alpha 60 degrees. Similarly, this is at alpha 90 degrees. So this is what the AC cyclo converter at different values of firing angle, right? So now this is for resistive load because the output current and the output voltage, they are in phase. Now, if I replace the load with the resistive inductive load, then I can see the current wave shape will lag the voltage wave shape by some angle, right? So let me replace the load with RL load now. So this is 2 ohm and 2 millihenry. So let me replace all the loads with the resistive inductive load, and let me show you the waveforms for this cyclo converter with RL load. So this scope is for 30 degrees. So here you can see this is 30 degrees, and now there is a change in the output voltage and output current wave shape. So you are going to observe there is a lag in the current with respect to voltage. Then you can see the negative peak here, and this peak is due to presence of inductor. So if I increase the value of inductor, the negative peak will increase, and there is reduction in the average output voltage or RMS output voltage, I can say, right? So now you can see positive half cycle and negative half cycle. This is for alpha equal 30 degrees. Similarly, you can see at alpha Similarly, you can see at alpha 60 degrees. So this wave shape will give the uh, values at alpha 60. So now you can see here. So this is 60 and the load is inductive load. Because of that, you are getting this negative and the current is lagging the voltage by some angle. Right? Similarly, you can see at alpha equal to 90 degrees. The last scope will give the value at alpha 90 degrees, right? So this is alpha 90 degrees, right? So in two input cycle is completing only one output cycle. That is why it is the output frequency is 25 Hz. Now you can see output voltage, output current at different values of firing angle at the same scope. So now this is for 30 degree, this is for 60 degree, and this is for 90 degree. And where you can see the negative peak here. And in first one cycle, it is completing only the positive half cycle. But for the other cycle, it is completing only the negative half cycle. So what is called reduction frequency division is 2 because the input frequency is 50 Hz. So frequency division 2, it is dividing by 2, which means the output voltage, output frequency is at 25 Hz. So same thing you can see here, right? Like that, there is a frequency division 4. So where you can see 1 by 50 by 4, that means 12.5 Hz. So which means in one 4 input cycle, you will get only one output cycle. So that is what I can say. And due to the complexity, I'm not going to explain that particular topic here. Right? So with this, I will stop here. Thank you.